Hello there, this is Shoot Socrates. Welcome to our 9th video in my series for multivariable calculus, Math 5C at Pasadena City College. So I'm super excited because today we get to actually perform a double integral and find its exact value. In our last video, we just found an approximation for a double integral over a rectangle, right? So today we will find a theorem that will look a lot like the fundamental theorem of calculus, but it is applied, of course, to a double integral. So it's called Fubini's theorem, and it is at the top of page 7. And I will see you there in 1 second. All right, here we go. So Fubini's theorem in 2 dimensions says that a double integral of a continuous function over a rectangle where x is from a to b and y is from c to d can be computed as an iterated integral. So there are 2 versions. The double integral of f over r can be expressed as the integral from x equals a to x equals b. There's a dx matching it on the right side, of another integral, the integral from y equals c to y equals d of our function, this time with the differential dy. Okay, so notice that dy matches with the y labels in what's called the inner integral, and dx matches the x labels in our outer integral. So the other form of Fubini's theorem is almost the same, except that the x's and the y's are reversed. Okay, so we have the same double integral can also be written as the integral from y equals c to d, dy on the right, of another integral, x from a to b, of the same function, dx. Okay, so dx and dy changed positions, and the limits with the labels also change positions. Okay, so how do you execute these computations, right? So this is where it's explained. The differential in the inner integral tells us the variable with which we are integrating. The variable in the outer integral is taken to be a constant when we perform the inner integration. Okay, so I extracted the inner integral in the first equation here. And what we have to do is we need to find an antiderivative. Okay, except in this time, we have 2 variables. So instead of little f of x, we have capital F of xy. Okay, but since the differential is y, it's dy, what we want is a function, an antiderivative, so that when we take the derivative with respect to y of this function, you'll get little f of xy. Okay, so this symbol, this derivative symbol, is actually inaccurate. Okay, what we really should have is what's called a partial derivative. So we want a function, capital F, whose partial derivative with respect to y is our integrand, little f of xy. Okay, so when we perform this derivative, we pretend that x is a constant, okay, because we are integrating with respect to y. That might bother you for a few minutes, okay, but rest assured, you will get the hang of it very, very quickly with just a little bit of practice. Okay, so let's go to Scientific Notebook and I will show you an example. It's going to be similar to the example in this file, but I changed some coefficients. I changed the domain a little bit, and I also changed the order of integration from that example, so that this way you see a dx dy in one of them and a dy dx in the other. All right, so let's go. All right, so here we go. We want to find the exact value of the double integral over r of the function sine of 3x plus 2y dA. Our rectangle r is from 0 to pi over 6 along x and from 0 to pi over 4 along y. All right, so let's set up both versions. Okay, we will only compute it in one way, but let's set it up in both versions. Okay, so the integral that we want can be written in two ways. Okay, now making the integral symbol is a little bit time consuming, so I have some prepared templates over here. So in the first version, x will go from 0 to pi over 6. And then, here's how I do it. I do a dx right away, and then I back up, and then I go to the inner integral. Okay, so this way, we can see exactly what the outer integral looks like. And we have a matching pair. X's in our limits, dx for our differential. Can't go wrong. All right, and how about the y? Okay, I might as well copy this since I already have a pi there. And all I have to do is change this to a 4 and change the symbols. Okay, I also have a template for y, but here we are. Okay, so this is now our inner integral. Again, y in the labels for the limits, dy are differential. So our function is sine 3x plus 2y. Okay, I guess we don't need that extra pair of parentheses. So there you go. That is a full-fledged iterated integral in the order we say dy dx. Okay. What's the other version of Fubini's theorem? So we reverse the x's and the y's. So y will go on the outside, dy. Whoops, I said y. And then on the inside, we will have the x's. So x will go from 0 to pi over 6. Then we have dx. And then we will have our function inside. Okay, so there you go. Dx, x is over there. Dy, y is over there. Okay? So Fubini's theorem says that the double integral is both of these values. So in other words, these two also have to be equal to each other. Okay, so before we actually perform the integration, let's go to GeoGebra and let's take a look at how this function looks like over this rectangle. Okay, so let's input sine of 3x plus 2y. Ooh, oh my. Ooh, okay. So of course, it looks like there's some kind of periodicity going on here. See how those waves seem to be repeating themselves. But yeah, it should be periodic in two directions, okay, along both the x and the y. But our domain is very small, okay? So we're going from x equals 0 to pi over 6. So x equals 0, x equals pi over 6. And then we have y equals 0 and y equals pi over 4. Okay, you see it? I don't. So we got to zoom in a little bit. Okay. And yeah, there's our rectangle. So actually we need to scoot a little bit. Move it. Okay, right there. So let me zoom in. Okay. So that is where our function is supposed to be restricted. Oh, except we zoomed in a little too much. We need to be able to see the function. Okay, I think that's a good view. And let's see. Still hard to see, isn't it? Okay, so here's why. Okay, we have all of this stuff which is hiding the stuff that we want to see. Okay, so let's hide everything. we're going to start over. Okay, remember we have what's called the surface command. Okay, and this is the syntax that we are going to use. Okay, but because we have a Cartesian function, z equals this, okay, we'll just put x here, y here, and then the function sine 3x plus 2y here. Okay, this has the advantage that we can restrict x and y. Okay, we only want to go from 0 to pi over 6. So first parameter x will go from 0 to pi over 6. Y will go from 0 to pi over 4. Okay, so that's what we're going to do. X first, then y, then sine of 3x plus 2y. Get out of the parenthesis, put comma. X will go from 0 to pi over 6. And y will go from 0 to pi over 4. Okay. Right. I don't know why it didn't like it the first time, but I retyped and there it is. Okay, so this is our surface, and we have the restriction. X from 0 to pi over 6, y from 0 to pi over 4. Okay, so this is the only portion of the surface, the function, that we want to look at. And if we look from above, where's our standard view? Okay, so here's x and y, x and y. So from above, it really does look like just a rectangle. Okay, but of course, it's a surface. Okay, so it's kind of like, looks to me like a piece of cloth that's draped over, like you have a rod over here. But from above, it just looks like a rectangle. Okay, now in the PDF, there are, remember, a double integral represents some kind of volume. In this case, it's a good interpretation because our function is always above the xy plane within this rectangle. Okay, if you make the rectangle a little bit bigger, okay, so let's say instead of pi over 6, we go all the way to pi over 2. Let's go crazy. What will the surface look like? Ooh, see, check it out. So some of it is now under the xy plane. Okay, from above, it still looks like a rectangle. Whee! There you go. It still looks like a rectangle, but it seems like half of it is above, half of it is below. So what would you bet? Would you bet that that double integral, if we go all the way to pi over 2, should the upper part completely cancel with the lower part? Will we get 0? Maybe we'll play with that later on. Okay, so we're only going up to pi over 6. Okay, there we go. So now to think of it as a volume, we really should have walls, okay, 4 walls representing the 4 sides of this diagram, okay? So one way to do that is to, again, make surfaces. So we can say like surface, and yeah, you know what? I will follow what GeoGebra did and just use U and V. Okay, so let's see. One wall will be where y is always 0. Okay, and then z will, okay, so remember we're making like a rectangle. Okay, so z will be v. Okay, x is going to go from 0 to pi over 6. So you will go from 0 to pi over 6. And what about z? Well, the maximum value of sine is 1. So v will go from 0 to 1. Ooh, okay, there you go. So here is one wall. Okay, one of 4 walls. Now, unfortunately, I cannot force GeoGebra to stop at that curve. All right, it has to be the domain of the surface function has to be a rectangle. Okay, so I can't say, could you please stop at, where will that be? At sine of 3x, okay, because y is 0. It's going to say, no, I can't do that. Okay, I have to make a rectangle. Okay, so we'll have to imagine that there are 4 other walls around this solid. Okay, and we're basically looking for the volume of that solid, right? So again, we have to pretend that this portion does not exist. Okay. All right, so let's continue. In the PDF, I did x on the outside, y on the inside in the computation. So let's do it the other way. So that's what we want to do. We will use this version. Okay, so the inner integral is this. Let's isolate it. Okay, here's a copy. All right, so we need to find an antiderivative for sine of 3x plus 2y. Our differential is dx. Okay, so of course, one reason I chose this example is we get to practice with u substitution. Okay, so the u will be 3x plus 2y. Okay, so of course sine of 3x plus 2, that's sine of u. Okay, so that's a good start. But we need to replace dx. Okay, so when we get du, pretend that y is constant. All right, that's the key step here. Y is on the outside. So in the inner integral, we'll pretend that y is a constant. Okay, so if that bothers you, okay, so here's something like a training wheel. Okay, whee! So if that bothers you, then think of this as 3x plus 2k. All right, there's no y. Okay, k is just a constant. Okay, so when you get du, yeah, you'll just get 3 dx. Okay, with practice, you're not even going to need that. Okay, so y is a constant, we just get 3 dx. Okay, so of course, dx is going to be 1/3 of du. Fraction, 1/3 du. Okay, so now what we need is an antiderivative. Okay, so I'll put the integral symbol there, and we have sine of u, and then our dx is 1/3 du. Okay, so that is the antiderivative we want to find. Okay, so antiderivative of sine is negative cosine. Okay, so quick check, derivative of cosine is negative sine. So we need to cancel the negative with the minus. So we need negative cosine u. No need to do a plus c. So of course, what we get now, oops, don't forget the 1/3. There's a minus 1/3 there. And we will replace u with 3x plus 2y. Okay. I should also mention that in basic calculus, you sometimes have the option of changing the limits before you, when you convert into u's. But because we are doing double integrals, okay, normally we just go back to the original variables, in this case, x and y. Okay. So that's what we have. And so we can now compute the definite integral, or the inner integral, I should say. This will be that antiderivative where we evaluate. So I have a bar over here from x equals 0. Copy this to x equals pi over 6. Okay, so there we go. And what happens when we plug in the endpoints? Okay, so starting with above, x is pi over 6. Replace x with pi over 6. I'm not in GeoGebra. And then subtract this antiderivative at plugging in x equals 0. So minus minus, we will just get plus. X is 0. So let's just make x go away. We just get cosine of 2y. Okay? And of course, let's simplify. We will get negative pi over, cosine pi over 2 plus 2y. Okay? We could simplify this further. We could use, remember the cosine alpha plus beta identity? Cosine alpha, cosine beta, minus sine alpha, sine beta. Okay? So that does have the advantage that, that does have the advantage, doesn't it? So let's try that. It's good to practice our trick. Simplify. So this is cosine of pi over 2, cosine of 2y, minus sine of pi over 2, sine of 2y. Okay? Cosine pi over 2 is 0, so that first term goes away. Sine of pi over 2 is 1. Okay? So we just get negative of sine 2y. Okay, so with that minus 1/3, we are going to get plus 1/3 sine of 2y. Okay, so let's summarize what we did. Thus, this becomes 1/3 sine of 2y, and we have plus 1/3 cosine 2y. There we go. So notice that there is no x anywhere here, anywhere here. And that's because we plugged in constants for x, pi over 6 and 0. So x is completely gone. We get a function which is only in y. Okay? So that is what we will plug into the outer integral. Okay? So let me copy this whole thing, which is what we were working on. Now plug this into the outer integral. Okay, so there is our next step. It's going to be the integral from y equals 0, y equals pi over 4 of this function. Okay, and we have dy also. We're back in basic single variable calculus. Okay, so we know how to do this. Simple u substitution, and remember your antiderivatives for sine and cosine. Okay, so shall we? What's next then? We can factor out 1/3, of course. And what do we have? For sine of 2y, the antiderivative of sine is negative cosine. Okay. Negative cosine of 2y. And then for cosine 2y, oops. We have a u substitution. So there's a 1/2. Okay, so quick check. Okay, I'll say quick check. When we take the derivative, cosine becomes minus sine 2y. 2 goes out, and the minus and the 2 cancels with a minus 1/2. Okay, so how about cosine 2y? That antiderivative is now plus 1/2 sine of 2y. Okay, again, quick check. The derivative of sine is cosine. So 2 goes out, cancels with 1/2. All right. And we evaluate from y equals 0, pi over 4. Okay. So you know what? It would look nicer if I use square brackets. Get rid of that. Yeah, that looks so much nicer. So y will go from 0 to pi over 4. Okay, and this is where a lot of us, me included, make mistakes because cosine of 0 is not 0, it is 1. Okay, it is so easy to make that mistake. All right, so let's plug in the upper values. Okay, so at y equals pi over 4, 2 times pi over 4, let's go ahead and do pi over 2, and this is also pi over 2. Okay, and then when we plug in 0, cosine of 0 is 1. Okay, so it's going to be minus minus, it's going to be plus 1/2. Sine 0, that's 0. So minus 0. Okay, so what survives here? Cosine pi over 2, that is also 0. Sine of pi over 2, that is 1. Okay, so we get 1/2 plus 1/2. I'll put that step. Okay, so that's gone. We have 1/2 plus 1/2. So that's just 1. Final answer, we get 1/3. Okay, and if I'm not mistaken, that is the right answer. Okay, so the volume of that solid that we saw in GeoGebra should be 1/3. Okay, seems like a reasonable answer. Remember that the top is 1. So, the base is a rectangle. Okay, the rectangle with length pi over 6, width pi over 4. Okay, so if that were a complete box and you ignore the surface, then the volume of the box will just be, okay, we have pi over 4, pi over 6 times 1. Pi over 4 times pi over 6 times 1. Okay, so that simplifies and approximates to 0.411. Ooh, okay. The solid should have smaller volume than that, okay, because that box is obviously bigger. 1/3, yeah, I believe it. 0.333, smaller than 0.411. Okay, excellent. All right, so let's play a little bit. So this was our problem, of course, and we did this version, okay, where y is on the outside, x is on the inside. Notice, however, that I took away the labels, okay? And that's because we're going to run this now on Maple, and Maple will not recognize the meaning of x equals 0, x equals pi over 6. It's not part of its syntax, okay? So at this point, I can just go click equals, and yes, the answer is 1/3. Okay, I did run it first before starting this video so that I would know if I had the right answer or no. Okay, we did the reverse order, and it's hiding down here. So come on in, please. Yeah, so there's the reverse order where we have x on the outside from 0 to pi over 6, y on the inside from 0 to pi over 4. Do we get exactly the same answer? Yeah. Okay, otherwise we can file a complaint with Professor Fubini. Okay, you're wrong. All right, so what did we do in GeoGebra? We said, what if we changed pi over 6 to pi over 2? Was that what we did? So, if it were pi over 2, what would we get? I don't remember anymore. Oh, yeah. So we thought, oh, maybe the answer should be 0. Okay, so it does look like the top of that solid and the bottom have the same volume. Okay, so remember this happens in calculus, right? If you integrate sine one period, the upper part cancels with the lower part. Okay, so that definite integral from 0 to 2 pi will be exactly 0. Okay, so yeah, and what if you keep going? Okay, so you go past pi over 2. So what would be a little bigger? How about up to 2 pi over 3? Okay, let's see what happens. We get, what are we going to get? Ooh, still 0. How interesting. How about up to all the way up to pi? What are we going to get? Ooh, back to 1/3. Okay, very interesting. We saw that negative portion, right? So how about we play with that? So that went up to pi over 2. Yeah, I believe it was pi over 2. And then what if we start a little before it? Okay, so let's start at pi over 3. Okay, yeah, let's try that. What are we going to get? Ooh, negative 1/3. Okay, so that's the portion that seems to be below the xy plane. Okay, so yeah, just like in basic calculus, a definite integral can have a positive answer or a negative answer, or it could be exactly 0. Okay, there's nothing wrong with any of those answers. Okay, it's just some kind of a number. All right, so wow, we are at the end of our video. So I hope you enjoyed that. Finally, some real multivariable calculus. So until next time, what are we going to do next time? I think, yes, we are going to do double integrals where the domain is no longer just necessarily a rectangle. Okay, so maybe it's a triangle. Okay, or maybe it's a completely different shape. Okay, so until next time, I hope you enjoy the rest of your day. I'll see you in our next video. Bye.